I'm going to create this setup from scratch, okay? So you can see how easily it's done. First, to make things easier, I'm going to just import my geometry, which I have in this folder here. The geometry here is in STL, and I've decided to use the fastback geometry. I haven't used the detail on the Modi because this is just for a demo purpose. But yeah, you can import any of the driver models that are available, okay? So I'm just going to simply select my geometry, drag it straight into my graphic view. I will import the geometry in millimeters to keep the scaling correct, okay? And take a few seconds to import the geometry, and as soon as geometry is imported, I'm going to go through each tab, which is the typical way to work in XFlow, setting all the different parameters that need to be, well, there's very few parameters that need to be set up, but we'll set them in an ordered way, okay? So here's my geometry loaded inside the graphic view, okay? This is going to be an external aerodynamics case, so I'm going to leave the kernel as 3D. I'm going to do a full 3D simulation. The flow model will be set as single phase, and the analysis type, like I've just said, is external, and we're not going to be simulating any thermal effects or anything to do with temperatures around the car, so we're going to leave this as an isothermal simulation, okay? For my environment, we're going to keep the standard virtual wind tunnel, which is the, well, we're going to keep the domain type as the standard virtual wind tunnel, which is the most well, the best one to use for this this application, okay? We're not going to set any acceleration laws on our domain. For the reference area, we know that for this driver model in particular, we know that the reference area is 2.148 square meters, okay? Why are we putting this in? Because then it'll help us to get the aerodynamic coefficients correctly, okay? To be able to get the drag coefficient, the lift coefficient, and the side force coefficient directly inside the GUI without having to do any external post-processing, you just need to give it the reference area and also the reference velocity. I'm going to be simulating this at 100 kilometers per hour, which in meters per second is 27.77. And finally, my wind tunnel, we're going to replicate the conditions used for the drive air, or I think I might have reduced maybe the Y direction just to make it run a bit faster. The positioning of the wind tunnel, I know this from before, so I just set it up quickly. It's 7 meters in X, 14.68 in Y, and 0 meters in Z. Okay, my wind tunnel is now positioned. I just need to set the correct dimensions to be able to see it correctly, which is 50 meters in X, 30 meters in Y, and 30 meters in Z. Okay, here we're going to do a full, well, most wind tunnel cases for the automotive industry, they like doing a full consistent simulation, trying to replicate as many real conditions as possible. So we're going to have a moving floor here, which is the moving belt you get in your wind tunnels. I'm going to set this velocity law of the moving floor again to match the velocity of the air. And finally, my velocity law, my airflow is going to be 27.77 meters per second in X, which is my wind speed. We're not going to simulate side wind or anything like that, so we're just going to keep it in X. Now, as soon as my environment's set up, I can now move on to the Materials tab. Here we have all the fluid properties, and by default in single phase, it's the default settings are air, and it's exactly what we're going to be simulating. So I'm not going to change anything here, but you have all the different fluid properties such as molecular weight, reference density, operating temperature, things like that. Okay. We now move into the geometry tab. Okay, I have already imported my geometry as my first step. I always like doing that first. Here you can see the 5 geometries separated on the project tree. Okay, we have our body, which in this case is the fastback. We have the front left wheel, the front right wheel, the rear left wheel, and the rear right wheel. Okay, I've called them, well, here the wheel is both the tire and the rim blended together. Okay, since we're going to be turning this, I'm going to do a simulation with rotating wheels. The tire and the rim is going to be moving at the same speed, so it doesn't make much of a sense to have it as different shapes. Okay. Once the geometry is imported and you've seen it, everything can be seen correctly, you can start applying the boundary conditions that need to be applied on your geometries. In this case, we're going to leave them all as walls. So then I'm going to jump to the wall model that we're going to use. Okay, if you remember in the introduction, I said that we have a wall function that takes into account separation due to pressure gradients. Okay, we always use this this wall model as well on our external aerodynamics cases in which we expect separation due to pressure gradients. Okay. To call this wall model, this wall model is being called the no-equilibrium enhanced wall function, so I'll set it on all my geometries. So like I just said, it will take into account all the pressure gradients, okay? I'll set that wall model on each of the geometries. Okay, so that's the wall model set up. Now, well, the body is going to be left as fixed, but like I've just said, the wheels are going to be spinning, okay? So, to be able to get the wheels spinning correctly, you have to have them spinning or rotating on a correct axis, okay? By default, when you import a geometry, the local axis of each of the geometries is set on the center of the fluid domain, okay? So this needs to be changed. Okay, so I'm going to do this for each of the wheels. It's very simple in XFlow. I'm lucky that I want my geometry to, well, my wheels are going to be turning around their center of rotation, and this is very easy. This can be easily done with XFlow. You just right-click on the geometry, you modify the geometry's CFG or center of rotation position, which I'll do here. Here, this little button here will automatically try and put the local axes of each geometry on the center of rotation or the center of mass. Okay, so I'll click this button here, and this will move my local axes to here. Just to check that, I want to see if this is done correctly. Yeah, it has been done because it's moved the local axis position. I'll just double check this here. Sorry, I clicked the wrong geometry. I moved the local axes of the, well, it doesn't matter. I moved the local axes of the body instead of the wheel. Okay, I meant to hit the wheel. I'll do it for the front wheel. Sorry for this small mistake. Modify CFG position. Following the same process as before. This button here will automatically calculate the center of mass or the center of rotation. Apply this. Again, I'll just double check it, show my local axes, and that's okay, perfect. Okay, I have my my axes for each of the wheels, for this wheel properly centered. I'll do that for the rear wheel as well, just once more. Modify CFG position, center of mass, apply, show local axis, just to check that, and again, it's done correctly. Okay, so now I've got my my local axis set up correctly. I need to establish my rotation law to this, okay? To be able to get these wheels turning, I need to change their behavior from fixed to, in this case, enforced. Once you change it to enforced, you're going to be asked for position laws or angular laws, okay? For this case, to get the wheels turning in the Z axis, I need to apply an angular law to Z, okay? This angular law, as you know, is the tangential velocity divided by the radius, okay? Seeing as the car is going to be moving at 27.7 meters per second, this is going to be our tangential velocity, and I know the radius from experiment. Well, I've got the data of the wheel radius, okay? XFlow, I'm going to directly write this here in the Z positioning, 27.77 divided by 0.3184, which is the wheel radius, okay? XFlow works in, the angular laws work in degrees, okay? So like this, it's in radians, so I need to quickly convert this to degrees, which is multiplying it by 180 and dividing it by pi. And this angular law will be time dependent, so I need to multiply all this by t, okay? I'm going to just see if this is working correctly. Before setting up or before running the simulation in the GUI, you can see if you've set an enforced motion on any object, you can see it moving. You just need to press the play button. So if I do that here, you can see how the wheel is turning in the direction and angular law that I've just given it to it, okay? You will need to do this, you will need to do the same for the rest of the cases, but seeing as I'm pretty tight on time, I won't do the rest, okay? I left this simulation running last night. Before moving on to the post-processing, to set up the simulation, the most important part, okay, you need to set your simulation time. For this case, as you saw in the experimental data we showed at the beginning when I showed the driver experimental test, we used the 1 second simulation time. We'll leave the time step mode for XFlow to calculate this automatically. And the resolution, you can apply any resolution that you want on the geometry. For this, you need to use our refinement algorithm. I'm going to use the adaptive refinements, so you can track correctly the motion of the wheels, and you can dynamically track the wake at the rear of the vehicle, okay? To do a very coarse simulation, I would have the body at, I don't know, 1 centimeter, I think is what I use, yeah, 2 centimeters, okay? Before that, you need to set a resolve scale for the fluid domain, which will be 128. And then you can start setting, this will be the resolve scale during the entire domain. And here you can establish your resolution on the geometries, okay? Like I've just said, I'm going to establish this to 2 centimeters on each of the geometries, both the car body and the wheels. You would have to do the rest, the same for the rest. And you establish a resolution for the wake, okay? In the simulation I left running over the night, I established the wake resolution the same as the car geometry, but you could use double or even half of this, okay? But I'm going to leave it at 0.02. If you wanted a more precise refinement of the wake, you just set this at 1 centimeter or 5 millimeters. Or if you don't want to take the wake so much into account, you can double it up to 4 centimeters or 8 centimeters, okay? And that's about it for your setup. You establish your frame frequencies to see how many visualization frames you want. And finally, if you want to do any averaging or things like that, they can be established quickly here, okay? Once that's done, you just press the Run Simulation button, which I'll do here in front of you, okay? Just before doing that, I'll make sure I leave this correct. And you hit the run. XFlow will ask for a path to save the simulation. I'll use this path here, and I'll call it live driver demo, which will be my simulation name. This will save the simulation in that folder, and that's it. That's my simulation saved, and that shows you how quick you can set up your simulation. Then if you want to define the name of the folder on which you want to save your simulation data, you can also do that. I'll have the same name for this, live driver, and that's about it. After that, you can hit your run button, and XFlow will start doing the pre-processing automatically. Here it's doing the it's calculating the sorry, it's not calculating, it's generating the domain and all the different levels of refinement, okay? Level 6 will be what's supplied on the geometry and the wheels and the wake, and level 0, which is what you're going to have on the far field, okay? That's about it for the live demo. Once this is done, okay, this simulation took about 12 hours to run on my laptop. Luckily, I've done this overnight, so then you can just, I'm going to load this simulation, which I have here. Driver air, open. Yes, I'll save the changes. Okay. Once the simulation is done, you just have to load your data. Okay. It automatically, if you have simulation data, it automatically asks you to load it. Okay. Here it's creating the domain based on the simulation data, and here you have all the simulation data loaded and ready to be post-processed. I'm loading it from my external hard drive, so it's taking some time. And here you have
Santiago, this
yes.
is Russ. I really hate to interrupt you because I'm sure we would all love to watch you continue even with the post-processing, but we do have a few questions for you that I would like to get answered.
Sorry, the live demo went slightly over time.
No, don't be sorry. It was wonderful. We love watching it.
Okay.
And I'm sure that we would all love to continue, but we do have some time limitations. So let me get to a couple of questions.
Okay.
First off, we have a question. How is geometry imported? We saw STL. Do you import STL only, or is native CAD data available also?
Okay, that's a great question. We have 3 different ways of importing geometry in XFlow. Okay, you can import an STP, which the geometry will be imported with in parametric format. You can also import it in STL, which I've just showed you now, and we also support importation of geometry in IGS. Okay, which is also another, I think it's another parametric format to be able to import geometry. That's the 3 geometry formats we can currently import in XFlow. I know there's going to be a lot of development to be able to develop CATIA, CAT parts and more
sure. So
geometry types that are appropriate from CATIA, yeah.
So is there any geometry modification utilities presently?
Yes, in XFlow, yes, you can direct, if you import it in the parametric format, you can play around with the geometry as much as you like. You can remove, delete, add surfaces, establish different boundary conditions to each of the surfaces, separate them, and anything like that.
All right, thank you. Another question is, after you've set up a model interactively, could it be run in batch mode afterwards with a modified geometry, or does it need to be set up from scratch again?
No, sure, you can run. Yeah, you can run simulations in batch mode, no problem. You just need to run them through command lines. If you have your different setups with different geometries or your different cases, if you create some command lines that will read each of the simulation projects, you can then automatically run it in batch mode, no problem at all.
All right.
Okay.
Thank you. Another question is, are there symmetry boundary conditions supported in XFlow?
Yes, definitely. For that, you need to. We have both symmetry and periodic boundary conditions. Okay, that you apply that to the flow domain. So yeah, that's not a problem. If you can. In wind tunnel default, you can't establish them, but if you use the generic rectangular domain, here you can establish different conditions on the boundaries of the domain, and one of them is symmetry.
All right, thank you. We've just had, I know we're running a few minutes over. If people have just a couple more minutes, we only have a couple of more questions that I would love to get through. So here's one. I'm just going to read it. It says, I saw mention of a transition model in the first slide. Is this a laminar to turbulence transition model? Can you please elaborate a bit?
Okay, this is currently not available on build 98, but as we speak, we're developing a laminar transitional model to be able to model laminar to turbulent transitioning. It will be hopefully available in the next build of XFlow, which will be released very soon, XFlow 2017.
Excellent.
So it's not currently available now, but we'll have it hopefully in a couple of weeks.
Excellent. Thank you. And then another question. In the thermal case, what is included in radiation? Ray tracing, participating media, spectral absorption?
I know we can model radiation. I haven't done many radiation simulations yet. So if we could, if I could answer that, I could check with the rest of the team to give you a very full detailed description of what's capable with our radiation model. We use a Monte Carlo radiation model, but I can't really get into much detail of what happens with it.
No problem.
If you permit me, maybe just to add an information on this. We use a Monte Carlo radiation model, surface to surface. So we calculate the radiation map at the beginning, and we use this radiation map for the entire simulation. So we use a surface to surface Monte Carlo radiation model with the radiation map calculated at the beginning.
Okay, thank you, Zaki.